Hello, everyone. Uh, I hope I am audible to everyone and my shared screen is visible to everyone. Okay, so very good afternoon to everyone who has joined with us for this lovely live session on NCRT solutions of ray optics chapter. As we know, NCRT is a base for your class board examinations, class 12 board examinations, as well as for those preparing for the NEET exam, that's the medical entrance exam. So we will be going in detail into all the NCRT exercise questions of the particular topic of ray optics today and discuss and understand the concepts which are essential for getting us to a good place to start. All right, so before starting, just a brief introduction about myself. I'm Saswat Mishra. I am currently a third year MBBS student at the All India Institute of Medical Sciences in Raipur, Chhattisgarh. Earlier, I was at IIT BHU, Indian Institute of Technology, BHU Varanasi, for one semester in engineering physics, from which I dropped out to pursue MBBS. Uh, I am from Odisha, Bhubaneswar, Odisha. So yeah, so that's all about me in a brief account. Uh, I guess we are good to start with the exercise questions of NCRT. I'll be going really slowly and we'll try to cover all the questions that are given in the exercises today. And at any point of time, if you guys have any doubt, then you can very well stop me or you can put it in the YouTube comments. So I'll very well see and reply to those doubts and we can have a fruitful discussion. So yeah, all right, saying that, let's keep our fingers crossed for a informative and nice session. And yeah, so let's get going started. And here's the first question. So let's read it. A small candle, 2.5 centimeters in size, is placed at 27 centimeters in front of a concave mirror of radius of curvature 36 centimeters. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Describe the nature and size of the image. If the candle is moved closer to the mirror, how would the screen have to be moved? All right. So after reading this question statement, let's figure out what are the information that has been given to us. So let's first write that. First, we have the size of the candle, which is 2.5 centimeters. That's the object size, right? So we can write the size of object of the candle, which is given to us as, let's, by h, the height is given. So I'm saying that h uh, is 2.5 centimeters. Next, we have the object distance. It's placed 27 centimeters in front of a concave mirror. So we have the object distance, all right, which by popular convention we denote by the letter U, as everyone must be knowing. U, which is 27 centimeters, but conventionally, as everyone knows, if I have a mirror over here, and it's the principal axis. And if the object is placed to the left side of the mirror, we take that as to be negative, right? So it would be minus 27 centimeters. Yeah. And also we have the radius of curvature as 36 centimeters. Radius of curvature we denote by R, right? Capital R, that is 36 centimeters. But again, what kind of mirror we have? We have a concave mirror, right? So if it's a concave mirror, the radius of curvature is again towards the left side, somewhere over here. So it will be a minus of 36 centimeters. All right. Always in ray optics, pay utmost attention to the sign convention. All right. Otherwise, the values in the equation would come out to be wrong, and you'll have a really great time figuring out what's going on. All right. So, as we know, it's very obvious that we have to apply the mirror formula here, and for that we need the focus, right? Focal length. We have the radius of curvature, and very well from that we can deduce the focal length as r upon 2, right? Which is minus 18 centimeters. That's right. Let's say the image distance is v, right? The image distance as the popular convention we will write as v. All right. So now it's pretty obvious. We have to apply the mirror formula, right? 1 upon v plus 1 upon u is 1 upon f. So we will put out the values over here. 1 upon v equals 1 upon f minus 1 upon u, and 1 upon f is minus, really sorry, minus 1 upon 18, and minus, we have here minus 1 upon u, right? U is minus 27. So minus 1 upon v plus 1 upon 27, right? So that, if you take LCM, it's 54 minus 3 plus 2, which is minus 1 upon 54. That implies your V comes out to be minus of 54 centimeters. All right. That is your image distance comes out to be minus 54 centimeters. So, what was the question? At what distance from the mirror should a screen be placed in order to obtain a sharp image? We obtain the image at minus 54 centimeters. That means the distance of the mirror, this is the answer to the first part, the distance of the screen from the mirror has to be, if I draw this out here, this is the concave mirror, and to the left side, we have to go 54 centimeters and place a screen to obtain a sharp image. All right, pretty clear, right? This is the first answer. Next question, next part of the question. Describe the nature and size of the image. Nature means if it's erect, inverted, real or virtual, like that. The nature of the image and the size of the image. We have been given the size of the object. So in comparison to that, what would be the size of the image? We have to describe that. So for that, it's pretty obvious, right? We have to find the magnification first, right? The M magnification, which is the height of the image upon the height of the object, which we have taken as actual, right? Height of the image upon height of the object. And for a mirror, it's equals to minus V upon U. That's everyone knows, right? So that implies your height of the image would be minus of V upon U into H, which equals, with the appropriate sign conventions, minus what's V minus 54 upon U, what's U minus 27 into H. H is 2.5 centimeters. And if we assume that it's standing erect, right, because it's not in the question, of course, the object will be erect above the principal axis. So it's again positive, right, into 2.5 centimeters. And this comes out to be minus of 5 centimeters. So from this, we see that the image would, the height of the object is 2.5, but the image is 5. That means it's magnified. It's double the size of the object. Yeah. And there is a negative sign over here. What does a negative sign imply? It's inverted. We have said that the object is above the principal axis, it's erect, so it's positive. So if the image comes out to be negative, it means it is inverted, right? So the object is magnified and inverted. All right. So that's the nature of the image. And the next part of the question is, if the candle is moved closer to the mirror, how would the screen have to be moved? So, if I just take you back to the basic gray diagrams for a concave mirror, uh, let's say this is the concave mirror. Just for your understanding, I'm saying, principal axis. While object is at infinity, you will have the image at the focus. All right. Now, if the object is somewhere beyond the radius of curvature, right? Somewhere beyond the radius of curvature, the image would be between the focus and the pole, right? Uh, if the object is here at the radius of curvature, then the image is also at the radius of curvature. And if the object is between the radius of curvature and the focus, then the image is beyond the radius of curvature. So from these illustrations, you can very well visualize that as the object position keeps coming closer to the concave mirror, the image keeps on going away and away and away. If the object is at focus, the image is very well at the infinity, right? You all know this. So, what's the question asking? If the candle is moved closer to the mirror, how would the screen have to be moved? The screen then has to be moved. Screen has to be moved, has to be moved away from the mirror, yeah, away from the mirror to obtain the image. All right. So I guess it's very clear the explanation of the first question. If there are any doubts, then I don't think there is any doubt as such now in this part. So yeah, that's great. So let's move on to the next question. Yeah. So coming over here, the second question. Let's read out the question first. The question says, a 4.5 centimeter needle, a 4.5 centimeter needle is placed 12 centimeters away from a convex mirror this time of focal length 15 centimeters. Give the location of the image, the magnification, what happens as the needle is moved farther from the mirror. Again, the same kind of question as the previous one. Only difference here is that this is a convex mirror. That's all. So yeah, so let's approach this. What have you been given? The size of the object has been given as 4.5 centimeters. The object distance is given, that is minus of 12 centimeters. The focal length of the mirror has been given as 15 centimeters. Now let's think sometime. We have a convex mirror, right? So a convex mirror has its focal length towards the right side. You all know this. So if it towards the right side from the sign convention, it will be plus of 15 centimeters, right? Yeah. So we have been given the focal length And image distance we have to find, which is asked in the question. So again, applying the same formula, 1 by v equals 1 by f minus 1 by u from the mirror formula, which is equals 1 upon 15 plus 1 upon 12, right? Which is equals to in 60. We have 4 plus 5, which is 11 upon 60. Sorry, 9 upon 60. So we have V equals 60 upon 9 centimeters, which is 6.7 centimeters, right? In the positive sense, right? So the location of the image would be 6.7 centimeters to the right side of the mirror, right? To the right side of the mirror, 6.7 centimeters as its positive. All right. Again, I'm asking the magnification. What will be the magnification be equal to? Minus V upon U, right? Which is minus of 6.7 V. What is the U? It is minus 12. And which is, if you solve it by calculator, it comes out to be some 0.56. All right. So magnification is 0.56. All right. And describe what happens as the needle is moved farther from the mirror. Now, for a convex mirror, if you see, as like we did with the previous one, uh, the image of a convex mirror is always towards the right side and it's a virtual image, right? And if you shift the object towards the mirror, then this image also comes towards. So if you shift the object away from the mirror, the image also moves away from the mirror. So you can also put some values in this equation, different values of u, and find out different values of v, and you'll find that for a convex mirror, if the object is moved away from the mirror, the image will also move away from the mirror, right? So as the needle is moved farther from the mirror, the image will also move away from the mirror in the opposite direction, of course. Uh, yeah, so that's the answer to the second question. I hope there are no doubts here. It's exactly the same as the first question. Only difference is that this was a concave mirror and here we had a convex mirror. That's it. So I guess here no issues. So moving on to the next question. This is the easy question to start with. Uh, let's read the question first. A tank is filled with water to a height of 12.5 centimeters. So the question says, I have a tank over here and it's filled with water up to 12.5 centimeters. All right. Yeah. The apparent depth of a needle lying at the bottom of the tank is measured by a microscope to be 9.4 centimeters. We are saying that we are visualizing from the top, okay, in the normal direction, okay, and I have a coin over here at the bottom of the tank. But if I see from here, okay, from top, if I see from above, I find that to me, the coin appears as if the apparent depth is 9.4 centimeters. The coin's position appears somewhere here, and this apparently to me, it appears as if it's at 9.4 centimeters. All right. The question is, what is the refractive index of water? If water is okay, let's first get done with the first part, right? Yeah. So I guess it's a pretty easy formula, as everyone must be knowing. We have been given the real depth, all right. Real depth is 12.5 centimeters, and the apparent depth we have been given as 9.4 centimeters, all right. So everyone, I guess, knows the formula, right? The refractive index of a medium, over here it's water, is equals real depth upon apparent depth, right? Real depth upon apparent depth, which is 12.5 upon 9.4, and this equals 1.33. If you put in the calculator, that's the refractive index of water. So that's the first part of the question. Next, if water is replaced by a liquid of refractive index 1.63, now we don't have water, we have some liquid with the refractive index 1.63, right? Up to the same height, up to same height means this stays as 12.5, right? The real depth stays at 12.5. By what distance would the microscope have to be moved to focus on the needle again? We are saying that earlier the needle was appearing to be here. That means the position of the microscope was here. But if I put the new liquid, let's say the position of the needle shifts somewhere here. I don't know where. Let's say I shifts over here. That's the new position. And for that, the microscope is also has to be shifted to a new position, right? So it's asking by what distance would the microscope have to be moved, right? So it's just asking this difference, right? It's asking this difference. What would be this difference? By how much distance does the apparent depth change, right? So we know this apparent depth, right? It's 9.4. And for the new liquid, if we found this apparent depth from this formula, we can subtract the two values and very well get the difference, right? That's the logic behind this question. So let's get going. So mu of the liquid is again the real depth, that is 12.5 over the apparent depth, right? What would be the mu of the liquid? It's given as 1.63 equals 12.5 over apparent depth. So the apparent depth you will find out as 12.5 upon 1.63, right? Pretty simple. I mean, on the calculator, we get the value as 7.67 centimeters. So the distance, so the question doesn't end. We have to find the distance through which the microscope has to be moved, right? So the difference would be the new apparent depth minus the initial apparent depth, right? So the new apparent depth is 7.67. Initial is 9.4. So the difference is 9.4 minus 7.67 centimeters, which is 1.73 centimeters. This should be your final answer, not this is your final answer, not this. All right? Always keep track of what's actually asking in the question. All right. So I guess this is also a pretty easy question. No rocket science over here. I guess students would have easily followed through the discussion. Uh, let's check if there are any doubts of students in the comment section. Uh, I don't think there is any doubt till now in the comment section, which is great. So let's start with the third question. All right. For any student joining late, you can watch the videos I mean, you can watch the video previous. You don't need to be live. You can also watch the previous part. And if you have any doubt, you can put it in the comment and I can reply it in the after checking it out. All right. So that's not an issue. All right. So let's start with the fourth question. All right. Yeah. So figures this A and B, this figure A and figure B, show refraction of a ray in air incident at 60 degrees with the normal to a glass air and water air interface respectively. Just saying in that figure A, we have glass and air interface. In figure B, we have water and air interface. And the incident ray is coming from air in both the cases. All right. And going into the denser medium, right? The glass or the water. Predict the angle of refraction in glass when the angle of incidence in water is 45 degrees. So it's the same. We have been given these two data, and from these two data, we have to deduce this. What would be the angle of refraction in this case, in the glass water interface? All right. So, seeing the question, I guess it's pretty obvious that it's a question from Snell's law, right? Yeah. So let's just start with what's given to us in the figure A and B. Let's start with figure A, right? In figure A, we have this is the angle of incidence, right? I think that is invisible for you. Yeah, this is the angle of incidence, and this is the angle of diffraction, right? So from the Snell's law, we can write for this case, for the first case, we have refractive index of glass with respect to air, right? Refractive index of glass with respect to air, that would be equal sine I upon sine R. That's the Snell's law, right? Sine I upon sine R. You have sine 60, and sine 35, right? Sine 60 is root 3 by 2, and sine 35 is 3 upon 5, right? And if you put the values and solve it in the calculator, it comes out to be 1.51, right? So this is the first equation. All right. Or in the first case, this is the first case. Let's write 1.51. All right. Now let's go to the second case, the second situation. The ray is coming from air into water. All right. So the refractive index of water with respect to air would be again sine 60, which is the angle of incidence, upon sine 47. All right, the angle of refraction. And this value comes out to be 1.184. All right, from calculator, this value comes out to be 1.184. Now, we need to find this thing, right? For the case, the ray is incident like this from water to glass, right? So this would be refractive index of glass with respect to water. Remember, uh, how do we write this thing? The incident ray is in which medium? Let's say it's in water, right? So the water would be above, and the glass into which the refracted ray goes into which medium, that would be below, right? We write the refractive index of the substance into which the refracted ray goes with respect to the medium in which the incident ray is there. All right. So refractive index of glass with respect to water is sine 45 degree upon sine R. Let's say this thing is R, right? Uh, This thing is R. Okay. So now we have to find this value. We have to find this value. So see, I will tell you a concept here. Many students get confused upon this, right? Look at this expression first, and this case. When we write sine I upon sine R, or like the sine of the incident angle upon the refracted angle, uh, is equals to this mu. Now, how to write this mu is sine I is in the numerator, right? Sine I is the numerator. So while writing the refractive index mu, you have to write the other medium in the numerator, right? I is the angle in the air. So first, while writing numerator, you will write glass in the numerator, refractive index of the glass in the numerator, right? This should be equal to refractive index of glass divided by refractive index of air. All right? It's reciprocal, right? Angle, the angle and the mu are opposite. Okay. If this is in numerator, this should be denominator. This should be in numerator. This is in the denominator. All right. So remember this trick, you won't get confused. Okay. So now let's apply that same thing here. We have 45 and R. So if I put here, this should be equal to 45 is in the numerator and 45 is the angle in the water. So here water will be in the denominator, right? Mu of water here will be mu of glass, right? Let's break down these two things also over here. This would be equal to mu of glass by air, and this is mu of water over air. Okay. So we have these two expressions, mu of glass over air, mu of water over air. We have to find mu of glass by water. So it's very obvious that if we divide these two things, glass over air divided by water over air, we will end up with this. So let's do that. So we will divide this by this. In other words, 1.51 divided by 1.184. 1.51 divided by 1.184. Right. So from that you can find the sine R is sine 45 is 1 upon root 2 multiplied by 1.184 upon 1.51, and so this value comes out to be 0.5546. So from calculator, the R value comes out to be 38.8 degrees. All right. So that's the answer. The concept here, which you should take in mind, is that the concept of for not getting confused again in such type of questions, you should always remember that whenever you write sine I upon sine R, okay, you have uh, different media over here, coming like this, getting reflected like this. This is I, this is R, this is medium 1, this is medium 2. Just do the reciprocal. I is in what medium? It is in M1. So you have to write the refractive index of the medium 1 in the denominator. And here, the numerator, the media 2 in the numerator. Okay. So just remember this concept and you can easily solve these questions. Okay. So I guess this question is pretty clear to all of you who have joined. Let me check again the YouTube chat section. Is there any comments? No, I don't think there are any comments. There's no doubt. So let's proceed over to the next question. All right. Yeah. Okay. This question. A small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeters. What is the area of the surface of water through which light from the bulb can emerge out? Refractive index of water is 1.33. All right. So let me first describe you the concept. I have a tank of water. Okay. So from this tank of water, I have a bulb over here. Okay. I have a bulb over here. I have water. So imagine this is the vertical line. This is the vertical line. Rays from the bulb will emanate in all directions, right? It's a point source, so from all directions, rays will come. This ray will come out like this, get refracted away because it's traveling from a denser to a rarer medium. So it will move away from the normal, right? In both directions. Like this, it will go out, like this, it will go out, like this. But at some critical angle, if that ray, this angle increases, and it falls at some critical angle, then the angle of refraction will be 90 degrees at that particular angle. And after that, any greater angle than that, it will suffer total internal reflection. All right, EIR or total internal reflection. So, for any observer from the outside of this liquid box, for any observer, the rays will only come out. Let's imagine we are viewing from above, right? So, like these rays are coming out, okay? But at some critical angle, when it becomes 90 degrees, after that, no ray will come out of the box, right? After that, all the rays will just go back inside into the box. So if you see from above, you can only see this part. This part of the rays are only coming to your eyes. All right. So if you see from the above, you will see a circle because this is a point source, right? It's a point source. So in all directions, if you see from above, you will see a circle of light. Beyond this circle, all the rays are going inside the box again. They're getting totally internally refracted, right? So we need to find the area of that circle which is formed. So let me make this diagram a lot simpler. In other words, what we have to find is, see, I'll take only that ray which falls at the critical angle, right? I will take only that ray which falls at the critical angle on both sides. Okay, so it will get refracted at 90 degrees the normal, right? 90 degrees at the normal. This should be I. So this should be I. This is I. So this is I. Right? Let's say this point O, this is A, this is B. Beyond this, if any ray goes, then it will get TIR, right? Internally reflected. So I'm not bothered about those rays. Now, this part is forming the circle if viewed from above. So we need to find the area or the radius of the circle, which is OA or OB, anyone. This is the radius of the circle, right? First, let's apply Snell's law here to this interface, right? I say sine I upon sine 90 degrees, right? The angle of refraction here is 90 degrees, which is equals to, uh, from the previous question, uh, I wrote I above, sin I above. So I'll write the refractive index of air first above. All right. So refractive index of air is 1 and refractive index of liquid is given as 1.33. Water, right? So from that, I can easily find sin I. Sin 90 is 1. Okay. This expression is 1. Sin I is 1 over 1.33, right? So that implies I equals 48.75 degrees. Okay, 48.75 degrees. So if this I is 48.75, this I will also be 48.75. And we need to find this radius for finding the area. And we have been given the depth as 80 centimeters. That means this length is given as 80 centimeters to us. Right. So it's very clear from simple trigonometry that if I find tan I, which is OA upon, let's say, point P, right? OA upon OP. That implies OA equals OP into tan I, which is 48.75 degrees, which is, and OP is 80, right? 80 to 48, tan 8, 48.75 degrees. And that comes out to be 0.91. All right, meters. This is 80 centimeters, which is zero point 0.8 meters, right? So 0.91 meters. So now we find the area. Area is pi into r square. What is r? That is OA square, right? So which is equals to 3.14 into 0.91 square, which is 2.61 meters square. So this is the answer. All right. So through this area of the liquid, if you view from above, so only through this area it will be illuminated, cycle of illumination. All right. Beyond this, you can't see any light from the bulb because all will be totally internally reflected. I guess it's clear to everyone. Yeah. All right. So let's go over to the next question. The next question says, a prism is made up of glass of unknown refractive index, right? Prism is made of glass of unknown refractive index. A parallel beam of light is incident on the face of the prism. The angle of minimum deviation is measured to be 40 degrees. What is the refractive index of the material of the prism? The angle of the prism is 60 degrees, right? So let's write first of all what all has been given to us. The angle of minimum deviation is given as 40 degrees. All right. Angle of the prism is given as 60 degrees. All right. And we need to find the refractive index, right? So let's say it's mu, right? Okay. So we very well know the relation, right? Mu is sine A plus angular minimum deviation by 2 upon sine A by 2, right? Which is equals to sine 60 plus 40 by 2 divided by sine 60 by 2. Sine 60 by 2 is sine 30. So this is 1.2 sine 30. So this goes over to 2. It is 2 sine 60, 40, 100 upon the 2 sine 50 degrees, right? So this answer comes out to be 1.532. This is the first answer. Pretty easy, right? Now, if the prism is placed in water with refractive index this, we have been given this, predict the new angle of minimum deviation. We have been asked this value again, right? We know this A is the same, 60 degrees, right? So again, we'll write the same thing, 1.33 equals sine 60 plus um, angular minimum deviation upon 2 divided by, this will be when sine 60 upon 2 is sine 30, right? So sine 60 plus dm by 2 is 2 times 1.33. So it's 2.66. So 60 plus dm by 2 is sine inverse 2.66. All right. So from here, you can easily calculate this angular medium deviation, right? From calculator, you can find this value multiplied by 2 and subtract 60 degrees from it. And the value comes out to be, the angular minimum deviation comes out to be 10.32 degrees. All right. So it's a calculation based question. Otherwise, the concept is pretty simple. The formula is pretty simple. All right. So yeah, till now, 6 questions gone. I don't think there are any rocket science here. Uh, Let me pause for a minute or two and check if there are any doubts till now in these 6 questions or any concept that needs to be repeated again. Then we can move over to the next set of questions, right? All right. So let's check the comment section for once if there are any doubts till now. Uh, no, I don't think there are any doubts till now. So let's move over to the next question. Yeah. So the next question here, it is simple question actually. Let's read through the question first of all. Double convex lenses are to be manufactured from a glass of refractive index 1.55. All right. With both faces of the same radius of curvature. That means we have a double convex lens to be manufactured. And this is suppose R1 and this is R2, the radius of curvature, and they both are same. Right? R1 and R2 are same. So what is the radius of curvature required if the focal length is to be 20 centimeters? Alright, so we have been given our focal length as 20 centimeters and R1 is equals to R2 equals to R, let's say, okay? And the magnitude, of course, is R, okay? And we have been given the refractive index is 1.55. Now, if you see in the rough diagram, for this face, this R1, this face, radius of curvature will be towards the right side, right? So this should be plus R. And for this face, radius of curvature would be towards the left side. So it would be minus R. The magnitude value both are same, but if you write with proper sign conventions, this should be positive, this should be negative. All right. So very well, there is the lens has to be manufactured. We have been given these values, so anyone can guess. We have to put the lens maker's formula over here, right? So what we know, the lens maker's formula 1 by f equals mu minus 1 into 1 upon R1 minus 1 upon R2, right? Pretty simple. So 1 upon 20 is equals mu 1.55 minus 1 into 1 upon R1 is R minus of 1 upon R2. 1 upon R2 will be minus 1 upon R and again a minus, so it will be plus 1 upon R. which is 0.55 into 2 upon R. So R would be equal to 0.55 into 2 into 20, all right, which is 22 centimeters. So this is the answer. We have been asked that what is the radius of curvature then? So the radius of curvature should be 22 centimeters. All right, it's a simple question. Easy, no rocket science over here. Let's move on to the next question, right? Next question says, a beam of light converges at a point P. I have a point P and a beam of light just comes and converges on it. All right. Now, a lens is placed in the path of the convergent beam 12 centimeters from P. 12 centimeters away from P, I keep a lens, all right, in path of the beam. This is the beam, and in its path, I keep a lens. At what point does the beam converge if the lens is a convex lens and if it's a concave lens? We have two kinds of lenses. We keep both of them, and what by what distance or at what point will be the new converging point of the beam? It's asking. All right. So let's first understand the beams are actually converging and forming an image at that point, right? Initially, at that point P, all the beams are converging. That means the image is a real image, right? And we don't know from where the rays are coming. They are all converging to that point. All right. So it would be a pretty expanded sort of thing. They are converging to this single point. That means the object would be a virtual object. Okay. Because normally, if a real object, we assume that the beams actually diverge from the object. But the actually in this case, the beams are, you know, uh, converging at a point. Okay, they're not diverging from the object, they are converging at a point. So we assume that the object is a virtual object. All right. So if the object is a virtual object, here the object distance is given as 12 centimeters because from P, from 12 centimeters, we keep a lens. So we have to assume that the object distance would be plus 12 centimeters as it's a virtual object. All right. So in the first case, a convex lens of focal length 20 centimeters. Convex lens means the focal length will be positive, right? Plus 20 centimeters. Any convex thing, it's always positive, right? So image distance, we don't know V. So 1 upon V minus 1 upon E, it's the lens formula, not the mirror formula, is equals 1 upon F. So that implies 1 upon V is 1 upon F plus 1 upon U, 1 upon 20 plus 1 upon 12, which is 68. So our V will come out to be 60 upon 8, which is 7.5 centimeters. And it's a positive sign. That means the rays will converge from this mirror 7.5 centimeters, right? Image will be formed 7.5 centimeters from this lens, sorry, not mirror, from this lens, 7.5 centimeters. But from the point it was kept 12 centimeters. From here it's 7.5 centimeters. So from the point you can calculate 12 minus 7.5, that will do you, right? Okay. Now the second question, concave lens. Concave lens, it would be negative focal length, okay, minus of 16 centimeters. So again, we apply 1 upon b equals 1 upon f plus 1 upon u minus 1 upon 16 plus 1 upon 12, 48 minus 3 plus 4. So we will get it as 48 centimeters. Okay, plus 48 centimeters. So from the concave lens, it will be 48 centimeters. The point P, this was 12 centimeters. So from this point, the convergence point will be 36 centimeters. All right. So yeah, so this is the answer. Guess this question is pretty clear. So let's move on to the next question. The next question is, an object of size 3 centimeters is placed 14 centimeters in front of a concave lens of focal length 21 centimeters. An object of size 3 centimeters placed 14 centimeters in front of a concave lens of focal length 21 centimeters. Describe the image produced by the lens. What happens if the object is moved further away from the lens? This is exactly the same sort of question we did in the first two questions, right? That was the case of a mirror. We have a lens over here. That's the only difference. So I don't think there is any theory explanation needed over here. So let's just get started. The object distance is minus 14 centimeters. Focal length, it's a concave lens, so minus 21 centimeters. 1 upon V equals 1 upon U plus 1 upon F, which is minus 1 upon 21 minus 1 upon 14, which is 42 and minus 5, right? So V would be minus 42 upon 5, which is minus 8.4 centimeters. Minus sign, so it will be left side. The image will be obtained 8.4 centimeters away and on the left side of the lens. All right. Since there is a negative sign, then the image, imagine for a concave lens, from the ray diagram, you can always imagine the virtual image is also always erect, right? The virtual image is always found on the same side and it's erect. All right, that's the nature of the image. And if you find the magnification, which is height of the image by height of the object. For lens, it is V upon U. For mirror, it was minus V upon U. All right. That implies height of the image would be height of the object, which is given 3 centimeters multiplied by V minus 8.4 upon U minus 14, which comes out to be 1.8 centimeters. So as you can see, 3, 1.8, so it's diminished, right? Now, if the object is moved further away from the lens, then yeah, just like in that case of a convex mirror, in a concave lens also, this is the object and this is the virtual image form. And if the object is moved away from the lens, the image will move closer to the lens. You can verify that using this equation, putting different values of u and obtaining different values of v. You can verify that if the object moves away from the lens, the image will move towards the lens. All right? Great. I think it's a pretty easy question. Like similar to the case first two questions. All right. So let's move on to the next question. What is the focal length of a convex lens of focal length 30 centimeters in contact with a concave lens of focal length 20 centimeters? It's combination of optical systems. All right. Always the powers get added, right? The powers get added, right? So the total power will be equal to the power 1 plus power 2. We need the total power. What is power? That is inverse of the focal length, right? which is 1 upon f1 plus 1 upon f2. In this case, 30 centimeters convex lens. So it will be positive 30 and concave lens of 20 centimeters. So minus 1 upon 20. Concave is minus, right? So this should be 60. This is 2 minus 3. So minus 1 upon 60. All right. So we have been asked what is the focal length, right? So the total focal length will come out to be minus of 60 centimeters. And okay. So if it's minus, minus implies the total combination will behave. This combination will again behave as a concave lens, right? Because it's minus. And as we know, the concave lens is a diverging lens, right? So the combination behaves as a diverging lens. All right, that is the question. This is the concept. The powers get added, right? Powers get added. All right. Let's move on to the 11th question. Ah, a compound microscope consists of an objective lens of focal length 2 centimeters and an eyepiece of focal length 6.25 centimeters separated by a distance of 15 centimeters. How far from the objective should an object be placed in order to obtain the final image? In two cases, the least distance of distinct vision in the first case, and second case, the object image is obtained at infinity. And what is the magnifying power of the microscope in each case? Okay, so let's first go with the first case. Focal length of the objective is given as 2 centimeters. Focal length of the eyepiece is given as 6.25 centimeters. And the distance between the two lenses is given as 15 centimeters. All right. So, okay. Now, what is the least distance of distinct vision given? 25 centimeters, right? It is 25 centimeters. This is the information given to us. So, if the image is formed at 25 centimeters, always remember we view the image of a microscope from an eyepiece. Okay. From the eyepiece, we view the object. The objective lens actually provides the magnification, but from the eyepiece, we view the object. So if the image is finally formed at 25 centimeters, okay, that means the image of the eyepiece is formed at 25 centimeters. So first we will write the lens equation for the eyepiece. Okay, for eyepiece, for eyepiece, we have the image distance V of eyepiece is minus 25 centimeters as it's a real image. You can see the image, right? It's a real image, minus 25 centimeters. Object distance, we don't know. Object is, let's say, some U of eyepiece. Now again, we apply this equation. Minus 1 upon UE is 1 upon FE, right? So from that, uh, you will get 1 upon UE as 1 upon VE, right? Minus 1 upon 25 minus 1 upon 6.25. Okay, which is minus 5 upon 25. So UE, we get it as minus 5 centimeters for the eyepiece. Okay, now image distance. Now this is the object distance for the eyepiece. What happens actually in case of a compound microscope that the object is kept first, the objective will magnify and form the image. And this image of the objective will act as the object for the eyepiece. And the eyepiece will form the image of this, and this we view it through our eyes. That's the actual working principle of the microscope. All right. So if this thing is the object distance for the eyepiece, this and the distance. Okay, and this is the distance between the objective and the eyepiece. All right, D. And for the eyepiece, we have the object distance here, -5. So this 5 centimeters here. And we said whatever image this forms is objective that acts as the object for eyepiece. So for objective, the image distance is D plus 5 centimeters, right? So for objective, the image distance is minus D plus 5. D was 15 centimeters, right? So D plus UV. So 50 minus 5, which is 10 centimeters. All right. So that's BE, and we know the F of objective is 2 centimeters. Again, 1 upon, sorry, this is VO. 1 upon VO minus 1 upon UO is 1 upon FO, right? So that implies 1 upon UO is 1 upon VO is 10 centimeters minus 1 upon 2. Right? So from that, you get UO as minus 2.5 centimeters. So that is the object distance. That is only asking how far from the objective should the object be placed. For the objective, we uh, should place it at minus, I mean, from 2.5 centimeters. All right. Okay. So this is the first case. In second case, the image is formed at infinity, right? So if infinity, that means what value is infinity? This value is infinity. This value in the second case, in B, this value is infinity, right? So this will be uh, this this 25 would be infinity. All right. So this would be minus 1 upon 6.25. Minus 1 upon 6.25. Okay. So this UE would be minus 6.25 centimeters. And for the objective, you have to subtract here 6.25. All right. So 8.75. Okay. 8.75. And here it would be 8.75. And this value would come out to be minus 2.59 centimeters. Okay. If the final image is formed at infinity, then the object should be placed at minus 2.59 centimeters. So we'll write both of the answers first here. For the least distance of distinct vision, we had uh, the object to be placed at 2.5 centimeters minus 2.5 centimeters. And for infinity, it was to be placed at minus 2.59 centimeters. All right. So this is the explanation. And the question again says, what is the magnifying power of the microscope in each case? Okay. So for the first case, when it's formed at the near point, okay, the formula for the magnification, you remember this formula, V naught upon mod U naught into 1 plus D by FE. All right. Image distance for objective, divided by the magnitude of the object distance, the objective, into 1 plus near vision, that is 25 centimeters, divided by the focal length of the eyepiece. All right. So for the first case, we had V naught is 10 divided by magnitude, that is positive value. So 2.5 plus minus 2.5, but we have to find the magnitude. So it is 2.5 into 1 plus 25 over FE. What was FE? 6.25 centimeters, right? 6.25. So this value turns out to be 20. And in the second case, the magnitude when at infinity, the formula for the magnification becomes uh, V naught by mod of U naught into D by mod of U, that is eyepiece. Okay, so these are the two formulas you should need to know. At the near point, this is the formula for the magnification, and at infinity, this is the formula for magnification. All right. So what was the V naught over here? 8.75, right? Divided by magnitude of U naught we found minus 2.59. So magnitude is positive into D is 25 divided by 6.25 UE. 6.25, right? So this value turns out to be 13.5. Okay. So these two formulas you need to remember. All right. So moving on to the next question. Uh, a person with a normal near point, that is 25 centimeters, is again using a compound microscope with the objective of focal length 8 millimeters, eyepiece of focal length 2.5 centimeters, and can bring an object placed at 9 millimeters from the objective, uh, 9 millimeters from the objective in sharp focus. All right. What is the separation between the two lenses? It's asking again D, right? So we wrote all the values. Okay. Uh, let's convert all of them to centimeters first with a single system of unit. Okay, fine. D dash we have 25 centimeters distance of near vision, right? So for the eyepiece, again the same equation at the near point. So for the eyepiece, the image will be formed at this point, right? It should be equals to VE. Okay, so this should be equals to VE. So 1 upon VE minus 1 upon UE is 1 upon FE. So from this, if you put the values, the UE turns out to be minus 2.257 centimeters. Right. Now, this UE, uh, now let's go to the objective. Okay. For the objective, if we apply 1 upon V naught minus 1 upon U naught is 1 upon F naught. Okay. You have U naught, you have F naught, so you can find V naught, which is 7.2 centimeters. Now again, the same relation, the distance is this sum of the distances, right? For the, what would be the distance? I said this is the objective, this is the eyepiece. So this is the image formed by the objective, okay? And this is the object distance for the eyepiece. So this sum of the distance will be the distance between the two lenses, right? So what's the value? 7.2 plus 2.27, right? Which is 9.47 centimeters. This is the value of D. This is the first bit. And what is the magnification of the telescope? At the near point, remember the formula, right? V naught, V naught into 1 plus near distance by 50, right? 7.2 divided by U naught, you find it as 0.9 into 1 plus 25 by 25, right? Which is 25 by 2.5. 25 upon 2.5, which is 8 into 11, that is 88. Right? Similar to the previous question of the first case, right? Numerical to previous table. Okay, all right. Moving on to the next question. A small telescope has an objective lens of focal length 144 centimeters, eyepiece of focal length 6 centimeters. What is the magnifying power of the telescope? You know, magnifying power of the telescope is just f naught by fp. So simple, right? By 6. This is 12 squared, right? 12 squared by 6, 2. So it is 24. The magnification is 24. And the separation for a telescope is f naught plus fp, right? These are direct formula based questions. So f naught plus fp, 144 plus 6, which is 150 centimeters. Okay. This value putting formula based questions. Next question, 15. Giant refracting telescope at an observatory has an objective length 15 meter, eyepiece focal length 1 centimeter, that is 0.01 meters. Okay. What is the angular magnification? Okay, again, magnification is f naught by fe, which is 15 by 0.01, which is 1500. All right. Now, the second bit, if this telescope is used to view the moon with the diameter, the image of the moon on is how much it's asking. Given the diameter of the moon is this much, and the radius of the lunar orbit is this much. Okay. So, uh, let's say, consider that what the objective, okay, objective lens is on the Earth, right? And the moon is actually at a very, very large distance. See, 3.8 in 10 for 8 meters. It's very, very large distance for the objective lens. The moon can actually be considered to be an object at infinity for this convex lens, right? And if that's the case, I'll draw the diagram. This is the objective at infinity. The moon is at infinity, and this ray is coming, and it will focus to the focus point, right? The focus point. Okay. So we will have the relation, uh, the diameter of the moon, the actual diameter of the moon divided by the distance of the moon from the objective lens, okay, which is just the radius of the lunar orbit that is given, is equal to the diameter of the object divided by the distance of the object from the lens. distance of the image from the lens. It's directly follows from the similar triangles, right? For similar triangles, the distance, the size, that is the diameter of the moon upon the distance of the moon from the lens is equal to the diameter of the image divided by the distance of the image. It follows from the similar triangle. That's the ratios should be equal, right? So that implies just put the values 3.48 into 10 power 6 divided by 3.8 into 10 power 8 is d dash we have to find divided by the distance is it's actually formed at the focus point, right? What is the focus of the objective? That is 15 meters. Yes, 15 meters, right? So from here, we find d dash as 13.74 centimeters. That is the diameter of the image which is formed. Okay, right? Right. So let's move on to the next question. This question is also pretty easy. Just need to know this formula, the angular acceleration, and that for an object at infinity, it will be a similar triangle with satisfying this relation, right? To remember this relation. All right. So next, moving on to the next question. Use the mirror equation to deduce that it's a conceptual question actually. Use the mirror equation to deduce that an object placed between f and 2f of a concave mirror produces a real image beyond 2f. What it's saying of a concave mirror, right? For a concave mirror, if we draw the ray diagram, uh, we very well know that the image will be formed beyond 2f, right? But it's asking to prove it using the formula. Algebraically, it's asking to prove. All right. Okay. So let's uh, get going. We know that for a concave mirror, focal length is negative, right? Because it's towards the left side. So f is less than 0 for a concave mirror. Now, the object distance you always take negative, right? Because it's towards the left. Now, the lens formula says 1 by f equals 1 by v plus 1 by u, right? So 1 by v will be 1 by f minus 1 by u. All right. Now, uh, for a real object, that is, which is on the left side of the mirror, u, it's given to be between f and 2f, right? The object is kept between f and 2f. So if we take the inverse, this sign would change. This inequality sign would change. And if we add on both sides, add on, no, first we do negative, we introduce negative sign into each of these. Okay. First, we introduce negative sign into each of these because we need to find this expression, all right? And now you add all by 1 upon f. If you add all by 1 upon f, we'll find this will be 0 less than 1 upon f minus 1 upon u less than 1 upon 2f, right? And what is this expression? This expression is 1 upon v. So 1 upon v less than 1 upon 2f, right? Uh, yeah. So uh, Uh, just wait a second. Up to here, the expressions are correct, and um, U lies between F and 2F. But okay, U lies between F and 2F, but actually this U and F are negative. Okay, so the sign would be reverse. Uh, U 2F F. Because magnitude wise this is not correct, this should be reversed, but actually these two are negative, right? So these inequality signs should also change. Okay, now if we reverse them, 1 upon u, reverse sign, this thing would change, and introduce again a negative sign, again change. Okay, and now add 1 plus f to all, so you'll have 1 plus f. If you add, it will be 1 upon f, 1 to f, less than 1 upon f minus 1 upon u, less than 0. And this thing is v, 1 upon v. 1 upon v turns out to be this. So from this, 1 upon v turns out to be negative, right? Which implies that v is negative and it's again greater than this thing, 2f. Okay, v is negative and v is greater than 2f. That means v lies beyond 2f, right? Okay, so first thing has been proved, right? Beyond 2f. All right, now let's move on to the second bit. A convex mirror always produces a virtual image independent of the location of the object. Right. Now for a convex mirror, we have F is positive, okay, U is negative. All right. Now if we write again the mirror formula, this thing 1 by V will be 1 by F minus 1 by U. Okay. And now what we can do is uh, 1 by F minus 1 by U. But we have this F is positive, U is negative. So this thing is positive. This is negative of negative. So this expression would be positive. So this is a step plus positive plus positive. So 1 upon V is always positive. That means V is always positive. V is always greater than 0. Okay. So it will always produce the virtual image irrespective of the location of the object. All right. So second point is proved. Okay. Now the third point. What does the third point say? Third point says the virtual image produced by a convex mirror is always diminished in size and is located between the focus and the pole, right? Okay. Now, again, same approach. F is positive, U is negative, right? Again, 1 upon V equals 1 upon F minus 1 upon U. We have U is negative. This thing is negative, so minus or minus will be plus. So it is 1 by F plus something. Okay. That means 1 by V will be always greater than 1 by F, right? Or V will always be less than F. So the image will be formed less than the focal distance. That means image will be formed between the focus and the pole, isn't it? If this is the pole, this is the F, this is 2F, less than F means it's always formed between this part, right? It will always be formed at this part. Okay. Now, this is proved, right? Now, for the fourth part, An object is placed between the pole and focus of a concave mirror, produces a virtual and enlarged image. Okay, we have to prove this. So how do we prove this? Let's start basically. Okay, concave mirror. So F has to be negative, U has to be negative, right? And from object is placed between the pole and focus. So it should be less than the focal length. Okay, it's less than the focal length, and again, it should be less than zero also because it's negative, right? So this is less than focal length, and both of them are negative. All right, so this is the expression is given in the question. Okay, so now 1 upon f for this equation, 1 upon f would be less than 1 upon u. All right, and this would be negative, right? Because this is negative. So if we invert it also, they will be negative. Now 1 upon f minus 1 upon u is less than 0. Subtract 1 upon u from both sides in this equation, right? Now 1 upon f minus 1 upon u is 1 by v, right? 1 by v is less than 0. So v is always positive. That means it is virtual image. Okay, since it's formed on the other side of the mirror, and u is less than 0, v is more than 0. So if you find the magnification would be minus v upon u, right? And minus, and this is also negative, so it will always be plus v upon u. Okay, and this should be always greater than 1 because v is more than 0, u is less than 0. Uh, so magnification will always be positive, right? So hence the formed image will always be enlarged. Okay, we have proved all the points over here, right? It's a good conceptual algebraic question, all right? Yeah. So next, moving on to the 16th question. A small, let's first look at YouTube, our comments. If there are any doubts, we can clarify. I don't think there are any doubts. So yeah, let's move on to the next question. Okay. The next question says, a small pin which is fixed on a tabletop is viewed from above from a distance of 650 centimeters. By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeter thick glass slab held parallel to the table? It says there is a table, there is a pin, and you have put a glass slab over here, right? And the glass slab is 15 centimeters thick. And you are viewing from a distance of 50 centimeters. By what distance would the pin appear to be raised? The pin, let's say, suppose appears to be here, apparent position. Okay, apparent position, suppose it appears to be here. By what distance it appears to be raised? This thing is asking. I think it's pretty easy, right? We had done a previous similar question based on this apparent depth, right? Apparent depth concept. Okay, refractive index is given. Okay, so let's solve it. It's pretty easy. What is the refractive index? That is 1.5 is what is the real depth upon apparent depth, right? So real depth is the depth of the slab, right? 15 by apparent depth. So apparent depth would be 15 by 1.5. 5 is 3 by 2, 30 by 3, that is 10 centimeters. So apparent depth is 10 centimeters. So from the surface of the table, it will appear raised by 15 minus 10, that is 5 centimeters, right? This is the answer. And the second part of the question, does the answer depend on the location of the slab? Does the answer depend on the location of the slab? I mean, this is the pin. Suppose I keep the slab here. Now this is the pin. Suppose I keep the slab like this, displace it to this side, to that side. Does this apparent depth depend on the location of the slab? Actually, for small angles of incidence, we are directly viewing from above, right? We are directly viewing from above, so the angle of incidence is practically zero. So for small angles of incidence, for small I, it's independent. Okay, remember, for small I, it will be independent. For larger I, again, you will have this refraction and this, there will be a difference, right? As you can see from the diagram. Okay, all right. For small I, it is independent. This real depth by apparent depth equals mu. This formula will be applicable. Okay, great. So moving on to the next question. Okay, this figure shows a cross section of a light pipe. These things are called as fiber optics. Okay, fiber optics made up of a glass fiber of refractive index 1.6. This is 1.68. Outer covering is 1.44, right? What is the range of angles of the incident rays with the axis of the pipe? That is, it's asking this I, for which total internal reflections inside the pipe takes place. Here, at this point, TIR takes place. What is the range of angles it's asking? All right. So write the equation for this point. For this point, let's say A, we have sine I, if TIR, then sine 90 degree. If I, then I is in the numerator, so I write the other part. What is the refractiveness of the outer covering will be in the numerator divided by 1.68. Okay, so from here you get the I dash, that is I dash, you get it as 59 degrees. This value is 1, right? So I get the I dash as 59 degrees. If this is I dash, it is 90 degrees, so this R will be 90 minus 59 degrees, which is 31 degrees, right? So this is 31 degrees. Again, apply this here. Sine I upon sine 31 degree will be equal to, I is for the air, so in the numerator it will be the glass, right? It is 1.68 by 1. So from here, sine I would be 1.68 into sine 31 degree. From here, you get the angle of incidence as 60 degrees, right? Okay. So, uh, let not erase this one. Yeah. So for the angle of incidence 60 degrees, if you increase this angle, if you increase little bit of this angle, then this will increase, then this will increase, and all will suffer TIR. This was the case where it was 90 degrees, right? Where it was 90 degrees. But if you little bit increase beyond this, all the rays will form TIR. So you can't go above this angle. So that is the maximum angle of incidence, which has been asked in the questions. Okay. Range of angle, that is, this is the maximum below this angle. Okay. What is the answer if there is no outer covering? Okay. If there is no outer covering in the second part of the second part, okay, for the second part, if there is no outer covering, then this mu would be 1. It's just air, and this is 1.68. Just apply the same thing. Sine I prime over sine 90 would be 1 upon 1.68. That implies I dash should be equal to uh, this. Okay, from here you can find the I dash, and then you can find R as 90 minus I dash. Then again you can put sine I upon sine R, that is 90 minus I dash is equals to uh, this, that is 1.68. Okay, from here you can again find this different value. Okay, this is the answer if there is no outer covering. If no outer covering, then this value is just 1. Okay, I guess that's clear with the question. All right, so next move on to 18th question. Okay, the image of a small electric bulb fixed on the wall of the room is to be obtained on the opposite wall 3 meters away by means of a large convex lens. I have a wall over here, okay, and I have a convex lens over here, a large convex lens. Here I have a bulb, okay, and I have to obtain the image over here. What is the maximum possible focal length of the lens required for the purpose it's asking? Okay, what is the focal length of this thing? And this total length is 3 meters. Okay, this total length is 3 meters. Now, this is, let's say, U, and this will be V, right? This is U, this is V. And now if I apply the lens equation, 1 by V minus 1 by U is 1 by F. From here, F is UV upon U minus V, right? Focal length would be UV upon U minus V. Now, if you actually, in mathematics, they'll teach you maxima and minima concept. Okay, maxima and minima concept, and we need to find this F max, right? For maxima, this U, I mean, this uh, F should actually, U should be equal to V magnitude wise. Okay, we learned in mathematics maxima, you take the derivative of this equation. This U and V should be equal, then only this equation will give you the maximum value. And we need only that, right? The F max we need. So if this U and V are same, okay, this U and V are same in this thing, the object distance and image distance are same. That means when it's true for a case of a convex lens, for convex lens, for convex lens, if U is V, the magnitude is same, then that is equals to 2F, right? That is at the radius of curvature. When the object is at the radius of curvature, then only the image is also found at the radius of curvature on the other side, right? So this U is equals to V, which is equals to 2 times of F max. Okay. So, but we know U plus V is given as 3 meters here, right? So U is 2F max, V is 2F max. So 4 times of F max is 3 meters. So F max would be 3 by 4 meters. Okay. This is the answer to this question. In general, you can remember, that's the concept you can remember. This F max is equals to this 1/4 of the distance. Okay, the given distance between the two dots. Okay, you can remember this concept. Okay, all right. So moving on to the next question. A screen is placed 90 centimeters from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeters. Determine the focal length of the lens. Okay, so we have been given distance between the screen and the object. Okay, screen is placed 90 centimeters from the object. That we denote by capital D, which is given as 90 centimeters. And the distance between the two locations of the convex lens. Image of the object on screen is formed by a convex lens at two different locations separated by 20 centimeters. That is given by small d as 20 centimeters. We need to find the focal length of the lens. This is a direct formula. The relation is capital D square minus small d square upon 4d. Right? This formula I need to remember. So if you plug in the values, 90 square minus 20 square upon 4 into 90, this comes out to be 21.39 centimeters. Okay. This is a direct formula based application. You need to remember this formula. Okay. All right. So moving on to the next question. Determine the effective focal length of the combination of two lenses in exercise 9.10 if 9.10. Okay, so let's move on to 9.10. This question, we found the this thing, right? When two lenses were kept, the powers were getting added. One was a convex of 30 centimeters and one was a concave of 20 centimeters, all right? Okay. So determine the effective focal length of the combination. We'll write it first. Left one was 30 centimeters, two was minus 20 centimeters. Okay. If they are placed 8 centimeters apart, now they have a distance between them. Okay. 8 centimeters apart with their principal axis coincident. Does the answer depend on which side of the combination a beam of parallel light is incident? I have this. Okay. And this beam is incident like this first on the convex lens. I could also have a situation like this. Beam is incident first on the concave lens. So does the answer actually change if in these two situations? Okay, that's the question. Okay, so let's get going. The basic approach. First, what we will do? First, we'll take one lens. Okay, we'll find where the image is formed due to this lens. First lens, image one. That will be the object for this lens, and again we'll find the image two, right? And we'll compare it in both the cases. All right. So in the first case, okay, let's say first we have the convex lens first. Okay, the incident ray first falls on the convex lens. Okay, so 1 by V1 minus 1 by U1 is 1 by F1, right? And U1 is infinity first of all, right? So that implies you get V1 as 30 centimeters. Okay, V1 is 30 centimeters. Okay, this is here, this is here. From here, 30 centimeters. And this distance is 8 centimeters. So for this lens, the object is actually towards the right side. So it will be a virtual object for the concave lens, right? Okay. For the concave lens, we will write again 1 by V2 minus 1 by U2 is 1 upon F2, right? U2 would be, this was 30, this was 8, so it would be 22 centimeters, right? Plus sign because it's towards the right side. Okay, 22 centimeters. F2 you know is minus 20. From that, we can find your V2 as minus 220 centimeters. Okay, now 220 centimeters from here and minus 220. That means it's a diverging, okay? It's a concave lens power, right? So ultimately, we get a diverging combination, okay, of minus 220. And from where, if we find a standard point, this is 8, right? So in between, it will be 4 centimeters. From here to 20 centimeters. So it will be 216 centimeters, 216 centimeters from the center of the combination. Okay, from the center of the combination. Okay, 220 centimeters would be minus 220, right? Minus 220 is this side, and here 4. So 216 centimeters from the center of the combination. Okay, so we'll just erase all of this, and for the first case, for the convex lens, if it's first, it's 216 centimeters. Okay, we'll just keep it over there. Now, first we'll take the concave lens. Second case, first we take the concave lens first. Okay, and apply again the mirror equation. This U2 is infinity now. Okay, so from here you find the V2 as minus 20 centimeters. This is the concave convex. From here it's 20 centimeters. This is 8. So for this it's minus 28 centimeters. Okay. So for the convex lens, 1 upon V1 minus 1 upon U1 is 1 upon F1. This is minus 28 centimeters. And this is 30 centimeters, right? So you find the V1 as minus 420 centimeters. From here, it's 420. From the center, it's 4 centimeters. So 416, right? Minus 416 centimeters from the center of the combination. Minus 216 minus 416. So what did we find? We found that, yes, it depends. Yes, it depends on the side of the combination, right? Minus 216 centimeters minus 416 centimeters. This is if convex is first, and this is if concave is first. Alright. So if it depends on the position, is the notion of the effective focal length useful at all? No, right? Because for different what or different configuration of the system, you'll get a different version of the image. So there is no use of finding an effective focal length, right? You have to analyze the situation individually for individual cases. All right. Okay. So the first bit is clear. Now the second bit, an object 1.5 centimeters, an object 1.5 centimeters in size is placed on side of the convex lens in the arrangement, on the convex side, right? On this case, the distance between the object and the convex lens is 40 centimeters. Now it's not infinity, it's 40 centimeters. Okay. Determine the magnification produced by the two lens system and the size of the image. Okay. So here we have U1 is given minus 40 centimeters. Okay. And you have F1. So from there you can find your V1. Okay. V1 is 120 centimeters. Okay. By V1 minus 1 by V1 is 1 by F1. Okay. Magnification is V1 by U1. It's a lens, right? V1 by mod U1, which is 120 divided by U1 is given 40, which is 3. Now, for the convex lens, your magnification is 3. Okay. Now, for the concave lens, U2 would be 120 centimeters plus the distance, right? 120 minus because it's on the same side, 120 and this was 8. So 120 minus 8, right? So 112 centimeters positive because it's on the right side. So from that you can find your V2 is minus 2240 upon 92. So that is M1 and M2 is V2 by mod of U2, okay, which is 20 over 92. So the total magnification is M1 into M2, right? M1 into M2, which is 60 over 92. Okay, so this is 60 over 92. Okay, I guess this is easy question, just a lengthy one because you have to analyze each case differently, each mirror differently. Okay, but it's actually just the application of the lens formula again and again. Okay, great. Next question. At what angle should a ray of light be incident on the face of a prism of refracting angle 60 degrees? Okay, so that it just suffers TIR on the other face. So if I draw a prism over here, this 60, it came here, it got reflected like this, and in this face, it is suffering TI, right? So it's asking this I at what angle should it be uh, put? Okay, this is R1, this is R2, and this is 90 degrees, right? It's TIF, it should be 90 degrees. So first, let's start at the point B, right? For point B, sine R2, because this is the incident for this face, right? By sine 90 degree is equals air is 1 divided by the prism. Refractive index is 1.524. And for this phase, for point A, we have sine I upon sine R1 is equals to the 1.524. If you multiply these two, you will get 1, right? And this is 1. So sine R2 into sine I is equals to sine R1. And you can see this is R2, this is R1. This angle should be 90 minus R1. This is 90 minus R2. If you add these, it will be 180 minus R1 plus R2. And if you consider this triangle, 180 minus R1 plus R2 is this angle, right? So this is 60 degrees. Okay. So 180 minus the sum of the other sides would be the other angle, right? So uh, this is R2, this is 90 minus R1. This is R2, this is 90 minus R2. If you add 180 minus this 180 minus this, okay, sorry. 180 minus this is the sum of these two angles, right? It should be equal to 180 minus 60 degrees, right? Because sum of this angle and this angle should be 180 minus this angle, right? So from here you find R1 plus R2 is 60 degrees, right? R1 plus R2 is 60 degrees. So from here, from this equation, you can actually find R2. Sine R2 is 1 upon 1.524. From here, you can find R2. And if you find R2, you can find R1. And if you find R1, then you can find sine I, right? Sine I would be equal to sine R1 into 1.524. And from here, you can find I, which actually comes out to be 29.75 degrees. Okay, is that great? Yeah, easy, simple question. So let's once look over the YouTube section. If there are any doubts, uh, till now, we don't find any doubts. So yeah, let's move on to the next question. Okay, now let's read out the next question. Hmm, okay. A card sheet divided into squares, each of size 1 mm square, okay, is being viewed at a distance of 9 centimeters through a magnifying glass. You have a card sheet and you are viewing it at 9 centimeters through a magnifying glass. All right, that's the question. And magnifying glass is always a converging lens, that is a convex lens. So focal length is also 9 centimeters. Okay, held close to the eye. So if it's a converging lens, you have a card here and you have the lens here, its focal length is 9 centimeters. Then all the rays which are emanating will actually pass to infinite, right? Okay. What is the magnification produced by the lens? Okay. Uh, and how much is the area of each square in the virtual image? So you have been given the object distance is minus 9 centimeters. Focal length convex, so it is 10 centimeters plus 10. So again, from the lens formula, you can find out 1 by u plus 1 by f. So you'll find the v as minus 90 centimeters. Okay. And the magnification would be v by u. Okay. So minus 90 by minus 9, which is 10. Okay. Magnification 10 means each side is magnified by 10. This is magnified by 10. This is magnified by 10. So the overall area will be magnified by 10 into 10 is 100 times, right? And the initial area was 1 mm square. So the final area would be 100 into 1, which is 100 square, which is 1 centimeter square. Okay. So the answer should be 1 centimeter square. Great. So next, move on to the second bit. What is the angular magnification of the lens? The angle magnification is d by uh, mod u, which is 25 upon 9, which is 2.8. Okay. And the third bit is asking, is the magnification in A equal to the magnifying power in B? Magnification in A we found out as 10, right? And the magnifying power we found as 2.8. So these two are not same, okay? Magnification is mod B by U and magnifying power is D by mod U, okay? The two quantities, when do you think will be equal? When B will be equal to D. That is, the image will be formed at the near point of the eye. Then only these two will be equal, okay? So in this case, these two are not equal, right? These two are not equal. Great. Next question. At what distance should the lens be held from the card chip in exercise 9.22 in the previous case in order to view the squares distinctly with the maximum possible magnifying power? That means it's indirectly asking that the image distance should be at 25 centimeters. Maximum possible magnifying power of the human eye occurs at the point of nearest vision. Okay. And you have f is given 10 centimeters. Again, it's asking u, right? 1 by b equals 1 by u plus 1 by f. From that, you will get your u as minus 7.14 centimeters. So the object should be placed at minus 1.74 centimeters away. Okay. Now let's see, calculate the magnification over here. Okay. Mod v by u, which is 25 divided by 7.14 minus 7.14, which is 3.5. Okay. That's the magnification. And magnifying power is d by mod u, right? 25 divided by mod of minus 7.14, which is again 3.5. Okay. So you can see very well that the magnification is equal to the magnifying power in this case. Yes. I told you here only when this V will be equal to D, then only these two will be same. Okay. Great. Next, moving on to question number 24. Uh, what should be the distance between the object in exercise 9.23, okay, and the magnifying glass if the virtual image of each square in the figure is to have an area of 6.25 square. Earlier it had 1 square, now it's having 6.25 square. That means the magnification is 6.25 is 25 side, right? So the magnification is 2.5 times. Okay, the M is 2.5 times because area is 6.25, so each side has to be magnified by 2.5 times. Okay, so now what is M? The M is V by U, right? Mod of V by U. So V should be equals to 2.5 times of U. Okay. Now you have your F, which is 10. Again, you put 1 by F is 1 by V minus 1 by U. So, and V you have 2.5 U, right? From that, you will have U is minus of 6 centimeters. Okay, and V is minus 15 centimeters. Okay, because V is 2.5 times of U. Okay, so now we've found out the distance between the object and the magnifying glass. Yeah, okay. Would you be able to see the squares distinctly with your eyes very close to the magnifier? If the object is placed very close to the magnifier, the image will be a virtual image, right? And virtual image cannot be seen by the eyes distinctly because it's formed at a distance of minus 50, at a distance of 15 centimeters, right? Which is less than the near point. Near point is 25 centimeters, but the image is formed at 15 centimeters. So the eye will be strained. So it will not be clearly visible. Okay? It will not be clearly visible because the eye can only visualize things clearly up to the near point, which is 25 centimeters. That's why it's called the near point of the eye. Beyond that, the object cannot see. Okay, I mean the eye cannot see the object clearly. Is that right? Okay. So moving on to the next question. That's a theoretical question now. Uh, okay. The angle subtended at the eye by an object is equal to the angle subtended at the eye by the virtual image produced by a magnifying glass. In what sense, then, does a magnifying glass produce angular magnification? Okay, it's saying that the object is producing some angle at the retina of the eye, right? Object is producing some angle at the retina of the eye, and the image which is formed by a magnifying glass, okay, by a magnifying glass in the retina is also producing subtending the same angle, okay, at the retina. Then, in what sense does the magnifying glass provide angular magnification? Okay, angle is remaining same. Then, in what sense does it provide angular magnification? Okay, the angular size of the image and the object are equal. Okay, because it's providing the same angle. So the angular size of the image, angular size of image and object are equal, right? When the objects are placed at the least distance of distinct vision, that is at 25 centimeters, when the object is placed, they can be viewed with the help of the magnifying glass. Okay. As the object moves closer than that distance, if it's less than minus 25 centimeters, then the angular size will increase. The magnifying glass is used because it provides angular magnification. Without magnification, it is difficult to place an object closer to the eye. So this meaning, this magnifying glass providing angular magnification, this means that if the object is brought less than 25 centimeters in front of the eye, nearer to the close point, then it will provide the magnification for the eye to visualize. Otherwise, without the magnifying glass, the eye can't see objects which are placed less than 25 centimeters in front of the eye. That is the sense of angular magnification provided by the magnifying glass. Okay. Now, in viewing through a magnifying glass, one usually positions one's eyes very close to the lens. Does angular magnification change if the eye is moved back? So the answer to this question is yes, the angular magnification changes. As the distance between the eye and the magnifying glass increases, the angular magnification decreases. Okay, so it's inversely proportional. Okay, it is inversely proportional. This is because the angle subtended by the eye is less than that the angle subtended by the lens. The lens is ahead of the eye, right? This is the eye and this is the lens. So this lens will be ahead of the eye at the retina. So this will subtend more angle than this. isn't it? This angle is of course more than this. Okay. So angular magnification will is inversely proportional. If this distance is increased, then the magnification will decrease. Okay. And but the angular magnification is independent of the image distance. It doesn't depend where the image is formed. It depends where the eye and the magnifying glass is kept. It depends on that. Okay. Next question. Magnifying power of a simple microscope is inversely proportional to the focal length of the lens. Okay. Then what then stops us from using a convex lens of smaller and smaller focal length? If we go smaller and smaller, then we should have a higher magnifying power, right? Because it's inversely proportional. But we don't use. What then stops us and achieving a greater and greater magnifying power? Okay, that's the question. Manufacturing lenses with small focal length is actually very difficult. Okay. When the focal length is small, there are chances of the production of spherical and chromatic aberrations. You remember these two things, spherical and chromatic aberrations. The image, the form of the image, the shape of the image will actually differ, or it will form a distorted sort of image. That is spherical aberration, and chromatic aberration means the colors will separate out due to refraction at the edges. Okay, so if it's a very curved one, then at the edges there will be refraction, and it will form a chromatic aberration. The colors will get dispersed. It will form a rainbow sort of thing. Different colors will be visible. Okay, for spherical and chromatic aberrations. Okay, so very much reduction is also not justifiable. There is no such reduction in the focal length of the convex lens. Okay, why must both the objective and the eyepiece of a compound microscope have short focal lengths? Okay, if you see for the compound microscope, the angular magnification formula is 1 plus d upon fp, right? And d is 25. Okay, so 25 upon Fe. And it can be inferred that if this Fe is small, it will form a higher angular magnification of the eyepiece. Okay, right. Now the angular magnification of the objective lens is 1 by u naught into f naught. So from here also, uh, while using a microscope, the object is kept closer to the objective lens, right? You have seen the objective lens literally touches to the stage where the object is kept. Okay. So the object distance is very less. This is very less. This thing is very less. Okay. As u naught decreases, this f naught also decreases. Therefore, in the given situation, if both we keep small, then the magnification will be very high. The magnification obtained will be very high. Okay. Now, when viewing through a compound microscope, our eyes should be positioned not on the eyepiece, but a short distance away from it for the best view. You directly don't touch your eye to the eyepiece. Okay? Just keep it at a slight distance from the eyepiece. Why? How much should be that short distance between eye and the eyepiece? We are unable to collect much refracted light when we place our eyes too close to the eyepiece of a compound microscope. Because see, if this is the eyepiece lens and you are viewing from here, the rays are getting refracted. Okay, so if you keep your eye very close, okay, if you keep your eye very close, then you will miss out these rays coming. Okay, they won't go inside your eye. But if you keep it at a higher point, you can increase your field of vision. Okay, so you can actually take into account these rays also which are coming. So we'll find the object a bit brighter and clearer if you see from a little distance from the eyepiece. Okay, the eye ring attached to the eyepiece gives the best position for viewing. If you see at the eyepiece, there is a eye ring attached to the eyepiece, okay? And you should keep it at that distance. It's actually made from the company only. So you keep it at that distance for appropriate proper viewing. Okay, all right. So next question. The angular magnification or the magnifying power of a 30x is desired using an objective of focal length this and eyepiece of focal length this. How will you set up the compound microscope? So you have F naught is given 1.25 centimeters. FE is given 5 centimeters. This distance of distinct vision, you know, it's 25 centimeters. And angular magnification is given 30x. Okay, which is the magnifying power. Now, magnifying power of the eyepiece is 1 plus d upon Fe. Okay, d is 25, Fe is 5. So this is 1 plus 5, that is 6. Okay, now for the objective lens into the eyepiece lens, the total one is multiplication is the total angular magnification, right? So the M0, M naught will be M by ME, which is 30 by 6, which is 5. Okay. Now we also know that this M naught is equals to V naught upon the object distance, right? So that implies V naught is minus 5 times of U naught. Okay. Now I thought minus 1 by U naught. So from that, you get your U naught as minus 1.5 centimeters. Okay. From this relation. Okay. And V naught would be minus 5 U naught. So 7.5 centimeters. The object should be placed 1.5 centimeters from the objective lens to obtain the desired magnification. Okay. Now for the eyepiece, okay, the image should be formed at near point, right? So VE is minus 25 centimeters, right? So from that, you find your UE as minus 4.17 centimeters. Okay. And the distance, the separation, the separation is V naught plus UE. Okay, the magnitude. Okay, so you get V naught as 7.5, and this is 4.17, which is Okay, I guess now we are back into the session. Really sorry for that. So let me read the question again. A small telescope has an objective lens of focal length 140 centimeters and an eyepiece of focal length 5 centimeters. What is the magnifying power of the telescope for viewing distant objects when the final image is formed at infinity, that is in normal adjustment, and when the final image is formed at the least distance of distinct vision, that is 25 centimeters. All right. Okay. So our telescope question, what we are given, the f0 is 140 centimeters, fe is 5 centimeters, and the least distance of distinct vision is 25 centimeters. Okay. So when the normal adjustment, we know magnification is f naught by fe, which is 140 by 5, which is 28. All right. Now, that's the first bit. Now, the second bit is asking when the final image is found at the least distance, the formula is f naught by fp into 1 plus fe by d, the reverse of the uh, microscope. In microscope, we have d by fe. Here we have fe by d, okay, which is 140 by 5 into 1 plus 5 upon 25, which is 28 into 1.2, which is 33.6. Okay, so we found out the two magnifications. All right, think pretty easy question. Great. So let's move on to question number 28. For the telescope described in exercise, the previous exercise, A means when the image was formed at infinity, what is the separation between the objective and the eyepiece? Okay, so in normal adjustment, the separation is just the sum of the focal lengths, right? So which is 140 plus 5, which is 145 centimeters. Okay, now if this telescope is used to view a 100-meter tall tower 3 kilometers away, what is the height of the image of the tower formed by the objective lens? Okay, now we had done this type of question in the microscope, in the moon question, right? Where we were seeing at a large distance the moon was there, and we found that there were similar triangles and the angle subtended was the same. Okay, so if the angle subtended is same, then we will find that the height of the tower divided by the distance of the tower from the objective is equals to the height of the image, okay, divided by the focal length of the image, a focal length of the objective. Okay, because this is the objective lens and at some distance there is a tower. Okay, draw the line. Image is like this, so these two are similar triangles. Okay, these two are similar triangles. This thing is formed at the focus. So this length by this length should be equal to this length by this length, right? Just normal similar triangle one case. Okay. So height of the tower is 100 meters, distance is 3000 meters or 3 kilometers. We need to find this h, and focal length of the objective is given as 140. Okay. So that implies we find the h as 4.7 centimeters. Okay. All right. So yeah, I think that's easy question. So B, okay. Now, what is the height of the image of the tower? We found the height of the image of the tower. What is the height of the final image of the tower if it is formed at this distance of distinct vision, that is 25 centimeters? Okay. So the magnification in C, magnification is 1 plus d by fe, right? So 1 plus 25 by 25, which is 2. 25 by 5, right? 25 centimeters, it's saying. Okay. So, yeah, 1 plus d by fe. So 1 plus 25 by 5, which is 1 plus 5 is 6. Okay. Height of the final image will be magnification into height of the this height, because this image will be acting as an object for the eyepiece. So h into m, that is 6 into 4.7, which is equals to 28.2 centimeters. Okay. All right. Next question. Okay. A Cassegrain telescope uses two mirrors as shown in figure 9.26. It's actually given inside the chapter, Cassegrain telescope image. This is actually what a Cassegrain telescope looks like. It has the objective mirror and a secondary mirror. The rays from infinity come into the objective mirror, reflected onto the secondary convex mirror, and then come to the eyepiece. This is actually a Cassegrain mirror. Okay. So a Cassegrain telescope uses two mirrors. Such a telescope is built with the mirrors 20 millimeters apart. If the radius of curvature of the larger mirror is 220 millimeters and the smaller mirror is 140 millimeters, where will be the final image of the object at infinity be? Okay. So Uh, the larger one is objective and the smaller one is the secondary mirror, right? And the distance between them is 20 millimeters. So D is 20 millimeters. Radius of curvature of the objective is 220 millimeters. Focal length of the objective would be 1110 millimeters, right? Now, radius of curvature of the secondary mirror is 140 millimeters. So the focal length would be 70 millimeters. Okay. Now, image of the object is placed at infinity. The object is placed at infinity, and the image which will be formed by the objective mirror. The objective mirror, for the objective mirror, image is at infinity. Object is at infinity, so image will be formed at the focal point. Okay. And that image will act as the object for the secondary mirror. Okay. So its image will be formed at 110 millimeter for the objective mirror. And for 110 millimeters, this was the objective and here was the secondary mirror, right? So from here it is 1110 millimeters, and for here it will be 1110 minus 70 millimeters and a virtual object because it's behind the mirror. Okay. So this U2 for the second mirror, it will be uh, for the second mirror, we will have uh, F1 minus the distance between them, minus the distance between them, that is 20. Okay, because this was here and this was the mirror. So this formed here and this distance is given 20. So this distance will be total this mirror distance, that is 110, because that's where the focus point is, that's where the image will be formed from infinity, and minus this 20. Okay, so which is 90 millimeters. Okay, now for the secondary mirror, for this convex mirror, if we apply the mirror formula, okay, for the mirror formula, 1 by V plus 1 by U is 1 by F. Okay, so 1 by V is 1 by F minus of 1 by U, 1 by 70 minus 1 by 90, which is 2 over 630. So V will be 315 millimeters. Hence, this is the final distance between the final image and the second mirror. Okay, that's the answer to this question. Next, 30th question. Light incident normally on a plane mirror attached to a galvanometric coil. This is the plane mirror. Retraces backwards as shown in figure. It goes, it strikes, and it retraces back. What is the displacement of the reflected spot of the light on a screen placed 1.5 meters away if this mirror is deflected by 3.5 degrees? Okay. If this mirror is by 3.5 degrees, then what is this D? Okay, this angle is 3.5 degrees. Okay, now the angle of deflection is 3.5 degrees, and this distance is given as 1.5 meters, right? The deflection experienced by the reflected rays is actually the twice of angle of deflection because, see, uh, I'll explain like this. Suppose you think this is 30 degree, so this angle will be 30 degree. Okay. Now, if I turn the mirror like this, okay, if I turn the mirror like this for some, let's say 15 degrees, 15 degrees, and this is 30 degree. So this initially was 90-60. So this will be 45 degrees. If this is 45 degrees, okay, and uh, this thing is 45, this is 15, and this angle is 90, okay, so this will be 45. This will be 45, okay, and if this is 45, then this will also get refracted at 45 degrees, okay, and if this is 45 and this is 30, and this angle is 15 now, okay, 50, and this is 45. So this total angle is 60 degrees, right? So if we this total angle is 60 degrees, okay, and uh, this is 30 degrees. So if I deflect the mirror by 15 degrees, this ray and uh, this ray, between this ray, the refracted ray and this ray will suffer deflection by 30 degrees. Okay, and that is 2 times of 15 degrees. So if I deflect the mirror by 15 degrees or by theta, then the this ray will get deflected from the original ray by 2 theta. Okay, so if it's deflected by 3.5 degrees, then the from the original ray, this is the original ray and this is the new ray. This angle should be 2 theta, that is 7 degrees, right? This angle should be 7 degrees. 7 degrees. Uh, this angle should be 7 degrees, and now it's easy. Tan 7 degree is d by 1.7. So you can find d, and this value actually comes out to be 18.4 centimeters. The trick is just to remember this thing that This angle actually gets deviated by 2 theta. Okay, that's the trick to remember. All right. So next, this is a very good question actually. This shows an equiconvex lens. This is the equiconvex lens of refractive index 1.5 in contact with the liquid layer on top of a plane mirror. This is a plane mirror. In between, we have a liquid, and this is the equiconvex lens. A small needle with its tip on the principal axis is moved along the axis until its inverted image is formed at the position of the needle. That means where is the image? There is also the object. That means the distance is actually 2f or the at the radius of curvature, right? The distance of the needle from the lens is measured to be 45 centimeters. The liquid is removed and the experiment is repeated. This liquid is removed and now the experiment is repeated. The new distance is 30 centimeters. What is the refractive index of the liquid? So let's see what's given. The focal length of the uh, 30 centimeters. Okay. Mm, okay. So the distance of the needle is measured. So the new distance when this liquid is not there, that means only this convex lens is there. Then you found the distance. This distance is 30 centimeters. Okay. And what did I say? That is 2f. That is at the radius of curvature. Okay. So the focal length of the lens is uh, 30 centimeters, right? Focal length of the lens is 30 centimeters. And this liquid acts as the mirror, okay? It comes and goes away. And the liquid acts as the mirror. And the focal length of the liquid, let's say the focal length of the liquid is some f, okay? Because see, this acts as a plano-concave lens over here, okay? This liquid acts as a plano-concave lens over here, okay? So the focal length of the total system is, when both of them are there, it is 45 centimeters, right? So 45 centimeters. Okay. Now the equivalent focal length is 1 over ft. 1 over ft is 1 upon fl plus 1 upon f liquid. So from that you find the f liquid as minus 90 centimeters. Okay. Now let mu1 be the refractive index. Okay. I say that this refractive index is mu1 of the liquid and the radius of curvature one face be r. This face, radius of curvature is r. Hence, for this surface, it will be minus r. Okay, because it's equiconvex lens. Minus r will be the radius of curvature of the other surface. Now, from the lens maker's formula, if I put 1 by f of the lens would be mu minus 1. Mu of the lens is given to us. Okay, that is 1.5. 1.5 minus 1 is 0.5 into 2 over r, right? So 1.5 2 cancel. So r is just FL, which is 30 centimeters. Okay. Now, and I assume this has mu. Okay. Radius of curvature of the liquid on the side of the plane mirror. If now this surface radius of curvature is infinity, this is minus r, right? And radius of curvature on the other side is minus 30. This is minus r, that is minus 30 centimeters. And for the liquid, if I find for the lens maker's formula, 1 upon f liquid is mu minus 1 into 1 upon minus r minus 1 upon infinity, which is 0. So mu 2 minus 1 is 1 by 3. Okay. Therefore, mu is 1 minus 1 by 3. That is 2 by 3. Wait, I think I made a calculation mistake. Mu minus 1 is uh, R is 30 centimeters. Okay, 30. And F liquid is 90. Okay. Yeah. So 1 upon 3. So mu is 1 plus 1 upon 3. That is 4 by 3, which is
বাইরের
1.3
মুভি
kg. So yeah. So that's the answer to this question. It's a great question. We just applied the lens maker's formula to this convex lens and this surface of liquid, thinking of it as a plano concave lens. Okay. So yeah. So I guess that's all the questions have been done. And if there are any doubts, let's check the Telegram. Let's check the YouTube for any comments or doubts. Uh, no, I don't think there are any doubts till now. So I guess, yeah, that's it. Uh, Hello, sir. Uh, Subhranshu, sir. Hello. Hello, Subhranshu, sir. Are you there? Hello. So I guess we finished with all the questions. Thank you for your patient hearing, and soon we'll be coming up with the next chapter, that is wave optics. So till then, happy learning. Bye bye.